So now we want to go ahead and besides using tables, we want to go ahead and see if there's other ways we could go ahead to calculate a limit without going through the trouble of putting in a table. So here we have something called the algebraic method. And we want to see if the limit exists, but without going ahead and doing all the table functions inside the calculator. So here is an example. We have a limit as x approaches 3 of x squared minus 9 over x minus 3. Now we could see that x minus 3, we're going to have a value at positive 3 that does not exist, which is where our limit is approaching. And we could go ahead and use a table and a calculator. We could go ahead and calculate all those and find the limit. But it's also, we could go ahead and look at the equation and see what's going on. We could see that the top, x squared minus 9, actually factors into x plus 3, x minus 3. And the x minus 3 on the top will cancel with the x minus 3 at the bottom, leaving us with just x plus 3 on the top. So therefore, even we can look at the limit. Even though there is an asymptote, we could see whether or not the limit exists at this function. So if we have x plus 3, we could go ahead and analyze that and get the value at 6. So we're going to go ahead and explore functions with the whole, functions we can factor, and try to find the limit and see if we can go ahead and do that rather than always use tables. Okay, so if f of x is continuous, where x is at a, then the limit of as x approaches a of f of x is equal to f of a. Okay, what this means is as the x value approaches a, then at that y value, that function exists. And this is a real useful definition, but for right now, we're just going to go ahead and assume that if the function is continuous, we could just simply plug in values into the function, and there we're good. This is not always the case if the function's not continuous at that point, but we'll explore that later. So let's go ahead and look at this example. So we want to look at the limit as x approaches 1 of 2x plus 1. And as x approaches 1, now we have no asymptotes and no holes. This is a polynomial line function. And if we go ahead and plug in 1, we go ahead and get a value of 3. So we could say the limit as x approaches 1 of this polynomial function is 3. And this is because 2x plus 1 is just a line. There's no discontinuities, there's no holes, there's no asymptotes, vertical asymptotes. So it's continuous. And it's good to know this because all our polynomial functions are continuous functions. And therefore we know there's not going to be any issues with any particular number as we go through and find the limit. And this is really useful to know as we go through finding limits. Right? Now, if we have a function with a hole, all right, and it's not continuous, so if you go ahead, plug in that x value, you get 0 over 0. Anytime you plug in 0, 0, there's a hole or some sort of asymptote going on. You could go ahead and make it continuous by factoring and canceling. And let's go back to our friend here, x squared minus 9 over x minus 3. If we go ahead to find the limit at 3, we do have a problem where that makes the denominator 0. We have issues, right? And if we plug it into the top, we also get 0, so we hit 0 over 0. So this signifies that we have an issue. But if we go ahead and factor it, as I mentioned, we go ahead and we have just the limit as x approaches 3 of x plus 3. And if we go ahead and plug in that 3, we get 6, as I mentioned earlier. So we could go ahead, if we can factor and cancel out and get rid of the issues in the denominator, then we get a nice value and the limit does exist. If you go ahead and go into the calculator and do a table, if you go ahead and get values from the left and from the right, you should get exactly the same answer as we did. All right, so now let's look at another one here. We have the limit as x approaches negative 2 of x squared minus x minus 6 divided by x plus 2. And again, if we go ahead and plug in -2, we do have a problem. We get 0 in the denominator. So we want to go ahead and see if we could factor the top and see if we could go ahead and get that denominator to cancel. And when we go ahead and factor the top, we get x minus 3 times x plus 2, and that x plus 2 cancels with the x plus 2 on the bottom. And therefore, we get the limit as x approaches -2 of x minus 3. If we plug in -2, we get -5. So our limit as x approaches -2 of this function is -5. All right. And then we can also have, rather than have limits that approach a number, we can have limits that approach infinity, which means either positive infinity or negative infinity. And this is really looking to see what happens as we approach the outer ends of this function. Does it go on forever? Does it have any horizontal asymptotes in disguise? Does it have anything that we can't see? So let's go ahead and look at a limit here of example 1, limit as x approaches positive infinity. So we're only going ahead and looking at the limit as it approaches positive infinity, which means we can really only examine the limit from the left-hand side. We can't approach positive infinity from the right-hand side because we don't know how far we have to go on that. So as we're approaching positive infinity, we're only looking at the left-hand side. So if we go ahead and look at this function as 3x over 7x minus 1, what we want to do is we can see that we're really looking at the ratio of the x values. The -1 is going to make little no difference one way or the other. As we go ahead and look at the limit as we approach infinity of 3x over 7x, we see that it's going to go ahead and get larger and larger on both sides. So this x really has no effect. It's going to be the same number on the top and on the bottom. So with the x taken out, we can look at the limit as we approach infinity. It's going to approach 3 over 7. Now, if you go ahead and graph this on your graphing calculator, this particular function, there is going to be a horizontal asymptote at y is equal to 3 over 7, which means as this graph gets closer and closer to infinity, it's never ever going to cross that horizontal asymptote that exists at 3 over 7. Okay, let's look at another one. Let's look at another limit function where we have the limit as we approach a negative infinity. Now we're looking at the limit coming from the right-hand side toward negative infinity. So as this graph gets smaller and smaller, we want to see what's going to happen at negative infinity. And we have 3x squared plus 2x divided by 2x squared minus 2x plus 1. And again, the real factors here are just our front numbers where we have both x squared terms. So that's what we're going to look at. So as we approach negative infinity, our x squared terms are going to cancel out. And again, we're approaching 3 over 2. So again, as we get smaller and smaller, there has to be an asymptote over at 3 over 2. Now let's go ahead and look at another example. We have 2x squared minus 1 over 3x to the 4th plus 2. And this is as x is approaching positive infinity. So again, we're really only looking at the front terms. That really, those constants don't determine where this graph is going. What really inquires where the graph is going is our x terms. So as we go ahead and look at just our front two terms, we end up with the limit as x approaches infinity of 2 over 3x squared. So as the bottom of this fraction gets larger and larger, that's going to make this fraction get closer and closer to 0. So the limit as we get closer to positive infinity is eventually going to end up at 0. So 0 here is our horizontal asymptote. All right. Now if we look at number 4 here, we're approaching positive infinity again. Again, we're looking at 2x cubed minus x minus 3 over 6x squared minus x minus 1. And again, we're only going to look at the front terms of this fraction. And as we do that, we have x over 3, And as x approaches infinity, the top now is getting larger and larger and larger, and the bottom is just a number. So therefore, this function is going to approach positive infinity since the value of infinity as it replaces x is in the numerator. All right. Now, if we look at number 5, we have kind of the opposite effect going on here. We have a negative in the top. So we have negative 5x cubed minus 4x squared plus 8 divided by 6x squared plus 3x plus 2. And if we look at those front two functions, the x cubed and the x squared term, we have negative 5x on the top and 6 on the bottom. Now remember, we're approaching positive infinity. So as x approaches positive infinity, is affected by this negative on the 5. And because that negative is in the numerator, it's actually going to go ahead and approach negative infinity as x gets closer to positive infinity. So in this case, it really matters where our x values are, whether there's a negative associated with it, whether or not it approaches negative infinity, whether or not it approaches positive infinity, or whether or not it approaches 0. So you just got to pay attention